In section 8.1, we explored exponential growth functions, which have the form of f of x is equal to a times b to the x power. These are exponential decay functions, which have the exact same form, but the difference here is that b is between 0 and 1. So it's less than 1 and greater than 0. So this would be what we would typically describe as a fraction. Okay, so if, and this is important, the way to tell the difference between a decay function and a growth function is if the b value here, the base of the power in the problem, if it's greater than 1, it's a growth function. If it's between 0 and 1, it's a decay function. Okay, and as we graph them, you'll see that there are some distinct differences in the graphs as well. So in this particular case, if I have this decay function, I know it's a decay function because the base is 1/5, it's less than 1. If I want to create an input-output table, I would again use inputs of -1, 0, and 1. Those are again the best. And actually with anything that you're going to graph that you're unsure of, a negative number, 0, and a positive number will be very informative to plug these in. In this case, it changes. This is the point where the graph changes from horizontal to vertical, is at this turning point from negative numbers to positive numbers. So when I plug -1 in here, 1/5 to the -1 power is 5, times 2 is 10. 1/5 to the 0 power is 1, times 2 is 2. And 1/5 to the first power is 1/5, times 2 is 2/5. If we go forward and we graph that, if you remember, the input-output table again was -1, 10, 0, 2, 1, 2/5. So at -1, I'm at 10. At 0, I'm at 2. And at 1, I'm at 2/5. So you see, this is very similar, but instead of being horizontal here as we approach negative infinity and vertical as we approach positive infinity, that relationship has reversed because of the inversing of the base of the power. So a growth function switched from horizontal to vertical. A decay function switches from vertical to horizontal as we move from left to right. Okay, again, if I have a negative leading coefficient, that again is going to take this shape and flip it over and make it that shape. Basically, it mirrors around the x-axis, it just flips over. If I do my input-output table, again, I'm going to pick the same numbers, -1, 0, and 1. 1/4 to the -1 power is 4, times -2 is -8. 1/4 to the 0 power is 1, times -2 is -2. And 1/4 to the first power is 1/4, times -2 is -2/4, which is -1/2. And when I plot that, I'm going to have a point here, and a point here, and a point there. And you can see that my graph is simply flipped over because of the negative leading coefficient. We had h and k in our exponential growth function, and you notice this function, the general exponential function, didn't change just because it's decay. The output changes, but the actual forms and the process by which you graph these hasn't changed at all. So we're going to do the exact same things we did in 8.1. I'm going to identify h and k. In this case, h is equal to 1. There's nothing being added on at the end. There's nothing over with the y, so k is equal to 0. And then I'm going to do an input-output table ignoring h and k. So if I do that here on my next slide, now my input-output table then is going to be for y is equal to 2 times 1/3 to the x power. K had a value of 0, and I just took h back out of the equation. Inputs are -1, 0, and 1. 1/3 to the -1 power is 3, times 2 is 6. 1/3 to the 0 power is 1, times 2 is 2. And 1/3 to the first power is 1/3 times 2 is 2/3. So at -1, I'll be at 1, 2, 3, 4, 5, 6. At 0, I'll be at 2, and at 1, I'll be at 2/3. And this is what my decay graph looks like. Now to finish the graph, all I need to do is shift it by h. In this case, h was 1, so I'm going to take each point. I'm going to shift it 1 to the right. This point moves 1 to the right. This point moves 1 to the right. And this point moves 1 to the right. That means my graph has simply moved 1 to the right. Okay, very simple. Again, it's the same thing we did in exponential growth functions, same thing we did in square root functions and cube root functions. So what does decay function model? Well, in financial terms, a decay function would model the depreciation of value. So an exponential growth factor would show the appreciation of something in a compound way. So for instance, a bank account that earns compound interest. And in this case, the decay function will model something that decreases the value, like depreciation. So we have the same sort of formula that we had before. In fact, you'll notice the only thing that's changed is where we had a plus here in the parentheses. Now we have a minus, because the rate is actually decreasing the value instead of before where it was increasing the value. And this quantity here in the parentheses is called the decay factor. The item in parentheses in the other function was called the growth factor. Here it's a decay factor. The way we'd use that in a real-life application. So if I bought a car for $22,000, that's my starting situation. That would go here where A is. So I know that the value of my car eventually will be the original value of the car, $22,000, times 1 minus my rate. So the value of the car decreases by 12.5% each year, 0.125 to the t power. And in this case, 3 years, time is 3. So y will be equal to 22,000 times 0.875 to the third power. And that's going to be equal to $14,738.28. So again, anytime you're using money, you should be going to decimal points. You should be doing 2 decimal points. And whatever you're going to do with the remaining decimal would be to round it to the cents part. That would be the standard for money. Okay, so that's how decay factors and exponential decay functions operate. They end up in decreasing values. So keywords to look for is decrease